Hello, it is Mrs. Pound, and we are going to wrap up Chapter 5 on Newton's second law of motion about force and acceleration today. So, our objectives are going to be to apply Newton's second law to explain why the acceleration of an object in free fall does not depend upon the mass of the object, and to describe what happens to the acceleration and the speed of a falling object when there is air resistance. So, let's start with free fall explained first. So let's say we have a 1 kilogram stone and a 2 kilogram stone, and we drop them out a window. What is the amount of force acting on them? We're going to use the equations F equals ma or W equals m times g, weight equals mass times the acceleration due to gravity. And we're going to analyze this. So for the first case, for our 1 kilogram stone, its weight is 1 kilogram times 10 meters per second squared, and we get a value of 10 newtons for its weight right here. For the 2 kilogram stone, when we do the math, we plug our values into the equation for W equals m times g, 2 kilograms times 10 meters per second squared, we get a value of 20 newtons. So what is their acceleration? It's 9.8 meters per second squared, or 10 meters per second squared. But why? Okay, so we would think that, okay, they have different forces, so why is their acceleration the same? So we're just going to rearrange the equation. A equals F over m, so acceleration equals force divided by mass, and we're going to plug the numbers in. So for our 1 kilogram stone, the weight or the force on it is 10 newtons. Its mass is 1 kilogram. When we divide 10 by 1, we get 10 meters per second squared. For the 2 kilogram stone, we put 20 newtons in for the force, 2 kilograms for the mass, and we get 10 meters per second squared. The same answer. Okay? The reason for this is that the ratio of the weight to the mass is the same. So if you have a little force and a little mass, that's going to be equal to a big force and a big mass because the ratios are the same. So that's why it works that no matter what it is on Earth, that it is accelerating at the same rate because of the ratio between the force and the mass. And this was proven by Galileo. Okay, he went up the Tower of Pisa, and he dropped two objects. He dropped a larger stone and a smaller stone, and yes, there was a little bit of air resistance, so the larger stone did hit a little bit faster, but it wasn't that much faster. It was just a few seconds faster. Um, they were hypothesizing that basically if something is 10 times larger, it will fall 10 times faster. And that is not what happened. So he was able to disprove the previous thoughts, but he didn't know why. Okay, he didn't know why, and we do know why now. So let's take a look at falling in air resistance because there was a little lag time in his experiment. To understand that, we need to know about terminal speed. This is the speed at which the acceleration of a falling object is zero because friction balances the weight. A lot like falling leaves. Falling leaves, they don't fall very fast. They don't continue accelerating. They just kind of flutter in the air. Terminal velocity is terminal speed together with the direction of motion down for falling objects. And we find that air resistance equals weight at terminal velocity. So F net is zero and there is no acceleration because the air resistance equals the weight. Now, the relationship between weight and air resistance, the greater the weight, the greater the air resistance needed to reach terminal velocity. So these skydivers, if there was much difference between their weights, the lighter individual would reach terminal velocity first, okay, before the heavier individual. But they will reach a terminal velocity. And it also depends upon the orientation of their bodies and things. Surface area also has an effect on the amount of air resistance of an object. That's why parachutes work, because they increase the surface area and it slows us down, stops that acceleration. Some animals make use of this as well. Flying squirrels make use of this. They have flaps of skin that they extend out so that they can fly through the air when they're in fact gliding. They can't really fly like a bird. The acceleration of an object decreases as it falls, even as its velocity increases because the air resistance builds up at higher velocities. So, terminal velocity is more noticeable at really high velocities than it is at lower velocities. So, you have to drop the objects from very high as opposed to closer to the ground in order to see these effects. And finally, if a rock is thrown downward and air resistance is negligible, the acceleration is still the same. It's still 9.8 meters per second squared or 10 meters per second squared. We don't add any acceleration by throwing it. We add some velocity by throwing it. In fact, we analyzed that in a previous chapter that we added velocity by starting it with a throw, but we do not add to the acceleration. So our objectives were to apply Newton's second law to explain why the acceleration of an object in free fall does not depend upon the mass of the object, and describe what happens to the acceleration and the speed of a falling object when there is air resistance. So don't forget your 5 questions and start studying for the test.